In this lesson, we will be learning about sequences. Now, generally speaking, sequences are a collection of objects that are in some kind of order. Now, mathematically, usually this is defined as a function whose domain is the set of positive integers, but we often don't use function notation for this kind of stuff. But how this works usually is we use subscript notation to denote what's going on here. So, for example, like A1 is the first term, A2 is the second term, A3 is the third term, etc. A sub n is the nth term. And to represent the entire sequence, we use curly braces around A sub n. So this means the sequence of all possible values. Let's start by listing the first 5 terms in the following sequences. So we have the nth term is given by -2 to the n power. So A1 is -2 to the first, or -2. A2 is -2 squared, or +4. A3 will be -8. A4 will be +16. And A5 will equal -32. In this sequence, our terms are given by 2n over n plus 3. So A1 will equal 2 over 4, or 1/2. A2 will equal 4 over 5. A3 will equal 2 times 3 is 6. 3 plus 3 is 6, so 6 over 6 is 1. A4 will equal 8 over 7. A5 is equal to 10 over 8, which reduces to 5/4. A sub n is cosine n pi over 2. So A sub 1 will be cosine of pi over 2. So look at your unit circle, look at pi halves, which is up here. The coordinates are 0, 1. Cosine is the x-coordinate, so this term is equal to 0. A sub 2 will be cosine of 2 pi over 2, which is cosine of pi. That's over here, and cosine is -1. A sub 3 will be cosine of 3 pi over 2, which is down here. Cosine is the x-coordinate, so this is equal to 0. A4 will be cosine of 2 pi, which is 1. It's over here. And A5 will be cosine of 5 pi over 2, which is the same as finding cosine of pi over 2, so once again we're back at 0. As you can see, the sequence is going to have a pretty nice pattern. It'll go 0, -1, 0, 1, 0, and the pattern will, this sequence of 4 numbers will repeat. Now, sometimes sequences can be defined in a way that's called recursively, and what this means is that the subsequent terms depend on the previous ones. So for this example, the first term is defined as 1, the second term is also 1, and the next term is given by, so think about this, A sub n, A sub 3 is what we're looking at. A sub 3 minus 1 is A sub 2, plus A sub 3 minus 2, so A sub 1. So the next term is found by adding the previous 2 terms. So in this case, A sub 3 will equal 2. A sub 4 is found by adding A sub 2 and A sub 3, so that is equal to 3. And A sub 5 is equal to adding up A3 and A4, that's 5. A6 would be found by adding 3 and 5, which is 8, etc. This is actually called the Fibonacci sequence, which is a pretty common mathematical sequence. Alright, this one we have A1 is given by 6, and AK plus 1 is 1/2 of A sub k squared. So my first term is 6, my second term is 1/2 of the term before, so 6 squared. So 6 squared is 36, half of 36 is 18. A sub 3 will be given by 1/2 of 18 squared, which is 162. A sub 4 will be 1/2 of 162 squared, which is 13,122. And these get large rather quickly. A sub 5 will be 1/2 of 13,122 squared, which is 86,093,442. Now, limits of sequences are defined much the same way as limits of functions. So what this formal definition says is the limit as n goes to infinity of a sub n is L if for every epsilon bigger than 0 there is a positive number m such that a sub n minus L absolute valued is less than epsilon. So think about this as a distance. This says the distance from a sub n to L is less than epsilon whenever your n is bigger than or equal to m. This is best explained with a picture. So what you have is you have 1, 2, 3, and the values of your terms are kind of bouncing around. And you think that your function is approaching this limiting value L. So somebody gives you a really, really small value epsilon. So this is L plus epsilon, L minus epsilon. And when somebody picks that epsilon, you can find a value m such that once you go past that point, all of your sequence values are within epsilon of the limit value. To determine whether the following sequences converge or diverge. So we are going to look at these more or less by inspection, but 1 over 2 to the n. So the first term is going to be 1/2, the second term will be 1/4, and then 1/8. So we're trying to find the limit as n goes to infinity of 1 over 2 to the n. And this is kind of the exact same thing as finding the limit as x goes to infinity of 1 over 2 to the x. This will equal 0 as the denominator gets larger and larger. 1 divided by a large number eventually will go to 0. Now if we have 2 to the n, the terms in this sequence are going to be 2, 4, 8, 16, and they just keep getting bigger and bigger and bigger. So this sequence diverges. Or you can say at the limit as n goes to infinity of 2 to the n is equal to infinity. I mean, this is a specific way to diverge. The terms go to infinity. They could also go to negative infinity, or they could bop around and not go to any particular place. Now, the first theorem we have to find limits of sequences is this. Suppose you have L being a real number, and f is a function of a real variable such that the limit as x goes to infinity of the function is equal to L. Now, if we have a sequence such that f of n equals a sub n for every positive integer, then the limit of the sequence is also L. So what you have is some function that approaches a limiting value L, and then you have the sequence that agrees with the function at all the integers, and so the limit of that sequence has to be the same thing. And this allows us to use things like L'Hopital's rule and other tools we use to find limits of functions, to find limits of sequences. Alright, so let's determine if this sequence converges or diverges. On this one we don't need to use the previous theorem. We can just find the limit as n goes to infinity of n squared over 2n squared minus n plus 5. So what you learned in Calculus 1 was that you could divide the numerator and denominator by the highest common power, so in this case, n squared. And that will give you the limit as n goes to infinity of 1 over 2 plus, 2 minus 1 over n plus 5 over n squared. And both 1 over n and 5 over n squared go to 0, so this limit is 1 over 2. Now, this next sequence is given by sine of pi n over 2. Now, if we were just to list out a few of the first terms, our sequence will look like this. We'll have a 1 followed by a 0, and then a negative 1, and then a 0, and then a 1, and then a 0, and then a negative 1, etc. We listed the first 5 terms for a similar sequence in one of the first examples. Now, in order to have a limit, the sequence has to eventually go to one defined place. This sequence bops around between 1, 0, and negative 1, doesn't ever make up its mind. This sequence diverges. And it diverges in a different way than the sequences that go to infinity. Alright, find the limit of the sequence where a sub n is given by the quantity 1 plus 1 over n to the nth power. So let's start by letting f of x equal 1 plus 1 over x to the x power, or also let that equal y. Now we learned how to find limits of this form using L'Hopital's rule back a few lessons ago. So we'll have ln of y is equal to x times the natural log of 1 plus 1 over x. And in order to apply L'Hopital's rule, we need some kind of ratio of the form 0 over 0 or infinity over infinity, and how we accomplish that is this. Let ln y equal ln of 1 plus 1 over x divided by 1 over x. And now we'll take a limit as x goes to infinity of ln y. There's a limit as x goes to infinity of ln of 1 plus 1 over x over 1 over x. And now as x goes to infinity, 1 over x goes to 0. So in the numerator we have ln of 1, which is 0. In the denominator, 1 over x goes to 0, so we can apply L'Hopital's rule. So we differentiate the function in the numerator. That will be 1 over the quantity 1 plus 1 over x multiplied by the derivative of the inner function, which is negative 1 over x squared. Now the derivative of the denominator is also negative 1 over x squared. And those negative 1 over x squareds cancel. So the limit that we have is equal to the limit as x goes to infinity of 1 over 1 plus 1 over x, which is 1. And thus, we have the limit as x goes to infinity, ln y is equal to 1. That limit can move inside the ln. So ln limit x goes to infinity, y is equal to 1. Exponentiate, and we have the limit as x goes to infinity of y is equal to e. And by the theorem about limits of sequences and functions, we have that the limit as n goes to infinity of a sub n is also equal to e. Alright, let's determine whether the sequence a sub n, where a sub n is 2n over 5 to the nth power plus 2, converges or diverges. If it converges, find its limit. So once again, we're going to define a function. We're going to let f of x equal 2x over 5 to the x plus 2, and we'll find the limit as x goes to infinity of this function. And right now this limit is of the form infinity over infinity, so we can apply L'Hopital's rule. So the derivative of the numerator is just 2. Now the derivative of the denominator, the derivative of 5 to the x is ln 5 times 5 to the x. And now our numerator approaches 2, our denominator just keeps getting larger, so this limit is equal to 0, and thus the limit as n goes to infinity of a sub n is also equal to 0. Now when talking about sequences and series, which we'll do in a later section, we are going to often use factorials. So the symbol n exclamation mark, which is not a very excited n, it's read n factorial, is used in counting arguments and all sorts of things, but just in case you haven't seen it, here's what this means. So this only works for integers, so whole numbers, 0 on up. By definition, 0 factorial is defined as 1, and in general, n factorial is all the numbers up to n multiplied together. So for example, 5 factorial is given by 1 times 2 times 3 times 4 times 5, which is equal to 6 times 20 or 120. And you can either list the terms ascending up to 5 or descending down from 5. 5 times 4 times 3 times 2 times 1. Same things as multiplication is commutative. Next, let's just discuss the difference between 2n factorial and just look ahead at what you have in part C, which is 2n in parentheses factorial. So this first one really just means 2 times n factorial. So what that means is 2 times the quantity, 1 times 2 times 3 times up to n minus 1 times n. Now part C, 2n factorial, means 1 times 2 times 3 up to n, and then n plus 1, etc., up until you get to twice n. So you should be able to see that part C is actually quite larger, and those parentheses make quite a big difference. Many of the theorems that you had for limits of functions are also true for sequences. So if we have two sequences whose limits are both equal to L, and we have a third sequence, C sub n, and there is a value n such that after you go past that value, your C sub n is sandwiched in between your A sub n and B sub n, then C sub n's limit is also L. And what this says is this, is you have your A sub n down here, and you have your B sub n above. And maybe it isn't always true, but eventually we'll draw C sub n around. Eventually, C sub n stays between those two. And if both the A sub n, which is this one, this is the black one, and the B sub n, which is the blue one, eventually go to this limiting value L, then so does the function that's stuck in the middle. So show that the sequence C sub n, where C sub n is given by -1 to the n times 1 over n factorial, converges, and find its limit. So what this -1 over n is going to do is make the terms in C sub n alternate between being positive and negative. So we know that C sub n is bigger than or equal to -1 over n factorial and less than or equal to 1 over n factorial. And the limit as n goes to infinity of both 1 over n factorial, that's equal to 0, and the limit as n goes to infinity of -1 over n factorial is also 0, and by the squeeze theorem, the limit as n goes to infinity of c sub n must also equal 0. Now, this squeeze theorem can also come up when you have sines and cosines, like suppose, for example, you had a sequence a sub n where the nth term was given by sine of, we'll say, n pi over 2 over n squared. So when you plug in successive values, you're going to have that these terms, sine is always between -1 and 1. So you always could say that -1 is less than or equal to sine of anything less than or equal to 1. So that would tell you that your a sub n is in between -1 over n squared and +1 over n squared. So it's just useful to know that you use sine's boundedness to determine what the lower and upper sequences are that sort of fence in the sequence that you're given. So we can also use the squeeze theorem to prove the absolute value theorem. So if you have a sequence of a sub n and the limit of the absolute value equals 0, then the limit of the regular sequence is also 0. And how we prove this is this. We use the squeeze theorem. So we consider the two sequences, negative absolute value of a sub n and regular absolute value of a sub n. Then what we have is that negative absolute value of a sub n is less than or equal to a sub n, which is less than or equal to a sub n absolute valued. And then since the limit as n goes to infinity of regular absolute valued a sub n is 0, so is the limit as n goes to infinity of negative absolute value a sub n is also equal to 0. And thus you've proven that the limit as n goes to infinity of regular a sub n is also 0. Now the next thing we're going to do is learn to write expression for nth terms of sequences and then determine if the sequence converges or diverges. So this is just pattern recognition. It takes a lot of practice and there can be many different patterns. So you have to see what's happening to your, in this case, your numerators and denominators. So we have the first term, the second term. Now it looks like the numerator is, in this case, you can think about that as 1 plus 1, 2 plus 1. So we can think about the numerators as being n plus 1. So with the first term, the numerator is 1 plus 1, which is 2. Second term is 2 plus 2, which is 3. 3 plus 2, which is 4. Now the denominator looks like it's the numberth term plus 2. So the best method that I have for this is just to make some guesses and then plug in n equals 1, n equals 2, etc. and check and see if your formula works for the terms you're given. So we plug in 1, we get 2 over 3. We plug in 2, we get 3 over 4. We plug in 3, we get 4 over 5. We plug in 4, we get 5 over 6. So that is the expression for the nth term. And now the limit as n goes to infinity of that a sub n will equal the limit as n goes to infinity of n plus 1 over n plus 2. You can multiply the numerator and denominator by 1 over n. So this gives us the limit as n goes to infinity of 1 plus 1 over n over 1 plus 2 over n, which is 1. Now this next one's a little bit more tricky. So the numerators appear to be powers of 2. We have 2, 4, 8, 16. So my numerator is probably given by 2 to the n. Now the denominators are 1 less than twice the term. So what I mean by that is the first term, so 2n minus 1. Let's just check that. When we plug in 1, 2 times 1 is 2, minus 1 gives us 1. If you plug in 2, 2 times 2 is 4, minus 1 gives you 3. So there is a formula for the nth term. And we are going to define a function, 2 to the x over 2x minus 1. And we're going to find the limit as x goes to infinity of 2 to the x over 2x minus 1. And we can apply L'Hopital's rule. The derivative of 2 to the x is ln 2 times 2 to the x divided by 2, and this limit is actually infinite. So our sequence diverges. The last thing we are going to discuss are monotonic and bounded sequences. So a monotonic sequence is a sequence where the terms are either non-decreasing or non-increasing. And what that means is that for non-decreasing, that successive terms are greater than or equal to previous terms, and for non-increasing is that successive terms are less than or equal to previous terms. So to determine whether this sequence is monotonic, let's just find the first few values. A sub 1 will be equal to negative for 5 plus negative 1, which is 4. A sub 2 will equal to 6. A sub 3, we're going to go back to 4. A sub 4, we're going to go back to 6. So this sequence is not monotonic. Now for this sequence, when we find, say, the first few terms just to see what's going on, B1 will be given by 3 over 3, which is 1. B2 will be given by 6 over 4, which is 3 over 2. And B3 is given by 9 over 5. So these terms appear to be gradually getting larger. So we're going to check and see, is B sub n less than B sub n plus 1? So B sub n is 3n over 2 plus n. B sub n plus 1 is 3 times n plus 1 over 2 plus n plus 1. Now we can multiply both sides by this denominator and that denominator, and the inequality will not flip because those quantities are positive, and that gives us 3n times 2 plus n plus 1 is less than 3 times n plus 1 times 2 plus n. At this point in time, let's cancel these 3's, and that will give us n times 3 plus n is less than n plus 1 times 2 plus n. And we're checking to see if this is true, so we still should have like a little question mark over this inequality symbol. Now distributing, we'll have 3n plus n squared is less than n squared plus 3n plus 2. And when we combine like terms, the n squareds cancel, the 3n's cancel, and we end up with 0 is less than 2, which is true. So our original inequality is true, and yes, this sequence is monotonic. And actually in this case, the sequence, actually the terms are strictly increasing. Now that's not the only way that you could show this. There's actually one more way to do so. And the way to do so is this. Define the function f of x to equal 3x over 2 plus x. And then find the derivative. And if you use your quotient rule, the derivative is equal to 6 over the quantity 2 plus x squared. And since f prime is bigger than 0, no matter what x is, this means your function f is increasing. And so thus, so is your sequence, is also increasing. And lastly, let's determine whether this sequence, c sub n equaling n squared over 2 to the n plus 1, 2 to the n minus 1 is monotonic. So the first term will be equal to 1 over 1, which is 1. The second term is 2 squared, so 4 over 2 squared minus 1, 4/3. So 1 and 1/3. And then C3 is equal to 9 over 7. C4 will be equal to 16 over, so 2 to the 4th is 16 minus 1 would be 15. Now this sequence is not monotonic because of this term. So this term, c sub 2 is greater than c1, and c sub 2 is also greater than c3. So this sequence is not monotonic. Now, sequences can also have properties called boundedness. Now, a sequence is bounded above if there is a real number m such that the sequence's terms a sub n are less than or equal to m for all n, and the number m is called the upper bound. And a sequence is bounded below if there is a number n such that this n is less than or equal to a sub n, and a sequence is called bounded if it's bounded both above and below. And a theorem called the bounded monotonic sequences theorem says that if the sequence is both bounded and monotonic, then it is going to converge. So we have some sequence that is fenced in below and above, and it's monotonic. So eventually it will converge. Not necessarily to that m value. I mean, that m could just be a general boundary, not the lowest such boundary. But eventually this sequence will converge. So to determine whether this sequence with the nth term is monotonic and whether it is bounded. So we already discussed this example. We know that this is monotonic from a previous example. And we know that the terms are gradually getting larger. So let's look for a lower bound. So since the terms are gradually getting larger, the first term, which is 3 over 3 or 1, that can function as a lower bound. And above, let's consider the limit as n goes to infinity of 3n over n plus 2. That's 3, so this is the upper bound. So this sequence is both monotonic and bounded because it's bounded above and below. Let's determine whether this sequence is monotonic and whether it is bounded. So it's pretty easy to convince yourself it's monotonic just looking at a list. So the first term, we'll plug in 1, that'll be 4 plus 1/2, or 4.5. The second term you'll plug in 2, 1 over 2 squared is 1/4, that'll be 4.25. The third term will be 4.125, etc. Basically, this 1 over 2n term is going to 0. So as n goes to infinity, a sub n is going to 4. And as you can see from the list of our terms, successive terms are going to keep getting smaller. So this series is monotonic. Officially, you could say that it is decreasing. And it is bounded. And we could say above by 4.5 and below by 4. All the terms are in between 4.5 and 4.